Welcome to the Explainer. So today, we're putting on our data detective hats. Have you ever noticed how two completely different things in our world just seem to move together in this mysterious kind of dance? Well, we're going to unravel exactly how things are connected by exploring the fascinating world of correlation. And don't worry, we're going to do all of this without instantly getting bogged down in heavy, complicated math. Let's get started. Okay, picture this mind-bending statistical trap right out of our source text. As summer heat rises, ice cream sales go through the roof. But at the exact same time, drowning deaths spike too. They positively correlate. But ask yourself, do ice cream sales actually cause people to drown? Is the ice cream the culprit here? Well, of course not, but the data definitely shows they move together. Here is our roadmap for the chapter. First, the meaning of correlation. Then, positive and negative relationships. Drawing the scatter diagram, Pearson's coefficient, the step deviation method, and finally, Spearman's rank correlation.
Section 1. The meaning of correlation, not causation.
So the absolute most crucial thing to grasp here is that correlation is just a means for systematically examining the direction and intensity of covariation between variables. Basically, it measures how things move together. But, and this is a massive but, it literally never implies cause and effect. Think back to our ice cream example. The reality is that a third variable, rising summer temperatures, is actually causing both the brisk ice cream sales and the higher number of people swimming, which unfortunately leads to more drowning deaths. Temperature is the hidden puppet master driving that high correlation. Section 2. Positive and negative relationships, and the types of relationships. The core rules for these relationships are wonderfully simple. Variables basically do one of two things. In a positive correlation, they move together in the exact same direction, in harmony. You know, like when your income rises, your consumption usually rises right along with it. On the flip side, we have negative correlation, where variables move in complete opposite directions. For example, when the local harvest supply of tomatoes increases, the price of those tomatoes drops. A really great way to visualize this is to think of the variables sitting on a playground seesaw. Do they move up together on the same side in a positive relationship, or does one plummet straight down to the ground while the other rises high into the air in a negative relationship? Keeping this mental image in your head is the perfect foundation for understanding data movement. Section 3. Drawing the scatter diagram, visualizing data. Before we even touch a calculator or crunch complex numbers, our first step as data detectives is to just look at the clues plotted out. A scatter diagram is an incredible tool because it visually presents the nature of an association without needing a single specific numerical value. If those plotted data points form a distinct, straight upward line, boom, that indicates a perfect positive correlation. If they slope downwards, it's negative. But if there's no correlation at all, the diagram just looks like a scattered, chaotic cloud of dots with absolutely no discernible pattern. Section 4. Pearson's coefficient, calculating R. Okay, visual clues are a great starting point to get a gut feeling. But now we need to bring out the mathematical magnifying glass for some exact precision. These are the unbreakable rules of Pearson's coefficient, simply known as R. This is a brilliant statistical tool that takes all that chaotic data and crunches it into a pure number with absolutely no units. It's not measured in feet or kilograms, it's just a pure number. And its value always lies between -1 and +1. If you calculate something outside that range, you've definitely made a mistake. An R of 0 means there is no linear relation whatsoever, while a high value, something close to +1 or -1, indicates a really strong relationship. Let's actually test this in reality with some fascinating data right from the chapter. Here we're comparing a farmer's years of schooling, that's our X variable, with their ultimate annual crop yield per acre, our Y variable. We really want to know, does education actually pay off out in the field? So we run that data through Pearson's formula, and it spits out the number 0.644. Now, what does that mean? Well, because it's positive and a relatively high number, we've got a strong positive correlation. We've mathematically proven that investing more years in education is directly tied to higher agricultural yields. When X rises, Y rises. Section 5. The step deviation method, simplifying calculation. But, what happens when our numbers are absolutely massive? It's one thing to calculate a few years of schooling, but what about tracking huge national economic data? Well, because we know from earlier that the coefficient R is completely unaffected by scale, we can use a clever shortcut called the step deviation method. We can shrink huge numbers like money supply in the thousands of crores down into manageable single-digit variables called U and V. By basically factoring out the zeros, we practically eliminate the heavy burden of manual calculation while still arriving at the exact same accurate mathematical correlation at the very end. It is such an incredibly elegant mathematical trick.
Section 6. Spearman's rank correlation, ranking attributes. Now for a really fun twist. What if the things we're trying to measure as detectives don't actually have numbers at all? What if we can't use a tape measure or a weighing scale? That is exactly where Spearman's rank correlation comes in. It lets us measure relationships between things we can only rank relatively. I mean, how do you measure fairness or honesty or beauty? You can't put a strict number on them, but you can rank them. Spearman's is also incredibly useful when a few extreme outlier values threaten to completely skew our traditional Pearson math. We simply rank the items instead of using their raw, chaotic numbers.
I'm going to leave you with one final real-world mystery straight from our source text to chew on. An epidemic hits some villages, and the government sends a team of doctors. But when the data comes back, the number of doctors sent positively correlates with the number of deaths. Does that mean the doctors actually caused the deaths? Or, kind of like the ice cream and the drowning, is there a hidden variable lurking in the shadows? Think about the timeline. Perhaps the doctors were sent to the absolute most terminal cases, or maybe the life-saving benefit of their presence simply took a little time to become visible in the data. The lesson here? Always look beyond the numbers. Thank you so much for joining me on this explainer, and keep your detective eyes open for the hidden correlations in your world.